All right, we're going to continue on in Unit 5, and we're going to talk about the different types of mixtures. So the lab that we covered, that we actually performed already, Lab 19, was dealing with the separation of mixtures. Remember in that lab, we were trying to separate, so our mixture contained sand, sodium chloride, and starch. So that was our lab mixture. Now each one of the components of that mixture can be classified as either suspension, colloid, or solution. So we're going to go through and define each one of these, and hopefully by the end of this page you'll be able to complete the rest of your lab. So a suspension, an example of a suspension would be charcoal and water. The solute particles are large and visible. It settles upon standing. Is it heterogeneous or homogeneous? Well, since you can see two distinct parts of this mixture, it's heterogeneous. When you shine a light through a suspension after you've shaken it so that the solute particles are suspended, if you try to shine light through that, it will block light. So it's opaque, so it blocks light. A suspension can be separated using filters. Okay, so another example of a suspension, if you remember in the 90s, there were these drinks called Orbits, and they had, it was kind of like a bottle shaped like this, but they had little balls, suspended flavor balls. They had orange and pink, and I have some in my office. If I think of it, I'll bring it to class the next time I see you. But those would be examples of suspensions. And over time, if you leave these Orbis drinks just sitting very still, they settle. So those flavor balls settle to the bottom. So whenever students come to my office, they say, "Ew, do you drink these?" No, they're like 10 years old, 10, 15 years old now. So I don't drink them. I use them for demonstration purposes. Okay. So the next type of mixture we're going to talk about is a colloid. An example of a colloid is whipped cream or milk. The size of the solute particles in a colloid is a medium size. It does not settle. So I'm not talking about rotten milk that has chunks. I'm not talking about that type of milk. I'm talking about good milk that hasn't been in your refrigerator for 3 or 4 months. So that would be a colloid. Since it does not settle, a colloid is homogeneous. The effect on light, if you try to shine light through a colloid, you'll see a Tyndall effect. So I'll write this down here. The Tyndall effect, light is scattered when it's shown through a colloid. So scatters light. And there's a good illustration in your textbook of this. Colloids can be separated using a semi-permeable membrane. So a semi-permeable membrane, remember we used that in lab. That was the dialysis tubing. So your cell is an example of a semi-permeable membrane. Contact lenses. So a semi-permeable membrane allows some particles to go through. Small particles can be transferred back and forth across this membrane, but large particles are trapped. Our last example of a mixture is a solution. An example is sugar and water. The size of the solute particles, small. Settling, does not settle. So we're talking about either a saturated or unsaturated solution. You have the max amount of solute dissolved and you don't have any settling. We're not talking about that type of settling. So this is just a saturated solution that doesn't have any solid at the bottom. The particles are small. The effect on light can be shown through a solution. So it's transparent. And I skipped heterogeneous or homogeneous. A solution would be considered homogeneous. Separation. When I talk about separations with solutions, a lot of students say, well, can't you boil it? That's technically not separation. When we talk about separation, we want to separate the solute from the solvent. If you boil the water, you no longer can recover the solvent. So you can't separate a solution. So that separation is not possible. So back to our lab mixture. We had sand, sodium chloride, and starch. Sand, is it a suspension, colloid, or solution? Think about our separation scheme. Remember, we filtered it and we were able to trap the sand. So sand is an example of a suspension. Sodium chloride. So we had our mixture, we filtered it, and then we used a semi-permeable membrane, and then semi-permeable membrane. Sodium chloride was on the outside, but it was still in water, so it wasn't separated from the water. That makes it a solution. Starch was trapped on the inside of that dialysis tubing, so that makes starch a colloid. So now you can complete Lab 19. Okay, so moving on in Unit 5, we're going to now talk about acids and bases. And your household is full of acids and bases. So on a daily basis, you come across acids and bases. And a lot of what we refer to, or shorthand notation with acids and bases, boils down to H plus and OH minus. So H plus is a hydrogen ion. That's shorthand for hydronium ion, which we'll see coming up. Shorthand for H3O plus. But we'll get into more of those details coming up. But the other component that we'll see is OH minus. This is hydroxide ion. And when we talk about acids and bases, acids contain the H plus. OH minus is what a base contains. It's a very simplified definition, and we'll learn ways to classify something as acids or bases better coming up. So, the first definition of an acid that we'll learn is the Arrhenius acid definition. And this is a substance that provides H plus and H2O. So HCl would be an example of an Arrhenius acid. When you put it in water, it ionizes completely and dissolves completely. It breaks up like this. So based on what you know about electrolytes from earlier in Unit 5, what would you say about HCl? Is it a weak electrolyte, a non-electrolyte, or a strong electrolyte? It is a strong electrolyte. All right. It's an Arrhenius acid as well because it produces H plus in water. HNO3, when you put it in water, it breaks up, it ionizes, and it dissolves to its component ion. Since it produces H plus, it's an Arrhenius acid. And since it ionizes completely, it's also a strong electrolyte. And the last one, H2SO4, known as sulfuric acid, this is H plus. And it breaks up completely so that SO4 doesn't have a hydrogen, it's just alone. Remember, that's sulfate ion. Now, is this balanced in terms of the hydrogens and the sulfates? No, it's not. I need to put a 2 here. Now, a lot of students often say, well, how are you balancing the water? The water isn't accounted for here. Remember that AQ means dissolved in water. So that's how we account for water right there. Okay, so these were all examples of Arrhenius acids. Now, an Arrhenius base is a substance that provides hydroxide and water. So sodium hydroxide, it's an ionic compound. And it produces Na plus hydroxide ion. So because it produces hydroxide ion, it's an Arrhenius base. It's also a strong electrolyte since it's ionized completely. Okay, so the next one, barium hydroxide. Breaks apart to give you barium ion and 2 hydroxide ions. So again, it has to be balanced. This is an example of a strong electrolyte. If you were wondering how I came up with that, because you're thinking about your solubility rules, good for you. Good for you. Barium hydroxide is one of these hydroxide salts that is soluble and it is a strong electrolyte, making it a strong base. If you put no reaction on this reaction, I would accept that as well, because based on what you've learned with your solubility rules, you've learned that salts of hydroxides are insoluble unless paired with group 1 or ammonium, and barium isn't that. So in order to classify this as a strong electrolyte, I would have to give you this information. So, those solubility rules are very good for generalizing, but there always are exceptions in certain cases. So I would have to provide this barium hydroxide information to you. So just keep on with your solubility rules. The next one, based on your solubility rules, makes sense. You would predict, if you didn't even know anything about acids and bases, that you would get potassium ion and hydroxide ion. And because it produces hydroxide ion, that makes it an Arrhenius base. Because it broke up, it's a strong electrolyte. So now we see the definitions of Arrhenius acids and Arrhenius bases. An Arrhenius acid is something that produces H plus in solution, and an Arrhenius base is something that produces OH minus in solution. While I am thinking about solubility rules, before we go on acids and bases, I want to go back to your rules. So let's go to page 6. I want to add an ion to solubility rule number 1. So salts that contain group 1 ammonium nitrate and acetate. So you guys remember acetate, right? They are always soluble. So any salts that have acetate in them will always be soluble, just like nitrate or ammonium or group 1. So if you came across any homework questions that dealt with acetate, hopefully that addresses those. All right, back to acids and bases. Okay, we just talked about the definitions. Arrhenius acid and Arrhenius base. An Arrhenius acid produces H plus in solution. An Arrhenius base produces hydroxide in solution. The problem with these definitions, they're very limiting. One reason they're limiting is not all reactions occur in aqueous solution. So not all reactions occur in aqueous solution. The other reason it's limiting is that H plus is so reactive, it doesn't even exist in water. Instead, what we see is that H plus, which is very reactive, reacts with water itself and produces hydronium ion. So, really what happens is we have, let's say we have HCl, which is hydrochloric acid. You have that in water. You know it's an acid. What really happens is H3O plus is produced, chloride ion. A lot of times you will see H3O plus written as H plus, and that's completely acceptable. But the original Arrhenius definitions don't account for that, so that's why it's a limiting definition. Broader definitions of acids and bases were developed after the shortcomings in the Arrhenius definitions were realized. And these are the Bronsted-Lowry acid and base definitions. So the Bronsted-Lowry acid This is definition of an acid is when an acid donates a proton. When I say proton, I'm talking about H+. So if you look at this acid reaction, ammonium plus water, the products are NH3 and H3O plus. If you look from left to right, NH4 has gone from NH4 to NH3, so it has lost a proton. So this is a Bronsted-Lowry acid. Ammonium is. Now, so Bronsted-Lowry, the currency is protons. So if a Bronsted-Lowry acid donates a proton, a Bronsted-Lowry base must accept a proton. So base accepts protons. If we look at that above reaction that I have, water accepted a proton, so that is your Bronsted-Lowry base. So in summary, Arrhenius acids and bases, your Arrhenius acid will produce hydrogen ion, bases produce hydroxide ion. The Bronsted-Lowry definition of acids and bases, acids are proton donors, while bases are proton acceptors. Okay, so we'll stop here for this lecture. You can go ahead and complete the homework problems that we've covered, for the objectives we've covered. I also want you to complete Lab 19. I want you to classify your sand, sodium chloride, and starch, which we already did in this lecture. And continue working on the rest of the labs that are due coming up.